Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into Chapter 2 from your textbook, starting with Section 2.1. Now, the first thing I want to mention before we jump into this section is that starting from Chapter 2, we're going to be starting into our investigation of linear algebra. So, in all of Chapter 1, we basically did a pretty thorough introduction of differential equations, terminology about differential equations, solution sets to differential equations, and a variety of techniques for solving first-order differential equations. As I mentioned a couple times, solving higher-order differential equations is very challenging unless you have a sort of more foundational sort of basis about what to expect of those solution sets. So to investigate that and to sort of build up some of that theoretical background, we're going to begin talking about linear algebra. Now, our initial foray into linear algebra is very, very basic here in Chapter 2. We're just going to start by talking about some of the major sort of objects and things that we use in linear algebra, which in this first section is going to be about talking about matrices. Matrices are going to be something that we're going to use a ton throughout this class. So a lot of this stuff is probably going to be review because we're going to go very sort of introductory here and just sort of review some of the terminology about matrices that you might have seen back in like a pre-calculus course or maybe a little bit in your multivariate calculus course. But we're going to just sort of remind ourselves about everything and then build from there. As we sort of work with matrices, we're going to investigate a lot of their properties, especially since they are sort of a new class of mathematical objects. So we'll get a chance to sort of talk about that. And then we'll be using matrices as one of the main sort of tools as we begin to explore the more theoretical side of linear algebra and start to learn about solution sets to different types of equations, starting with systems of linear equations, and then eventually building to linear differential equations. So for the next couple weeks, we're going to be just focusing on sort of linear algebra. We might hear a mention or two of differential equations, but pretty much we're going to be leaving that for right now, focusing on the linear algebra side of our course. So, matrices, definitions, and notation. So, first of all, a matrix is simply a collection of mathematical objects. Usually, matrices are made up of real numbers, but they could theoretically be made up of real numbers, complex numbers, functions, other matrices, any mathematical objects, as long as it's organized in a row-column format. So matrix is just a collection of mathematical objects in a row-column format. Each individual object is called an element of the matrix. So the things that make up your matrix are called elements of the matrix. We have notation that basically lets us pick out a particular element. So if we let A be a matrix, you'll notice also it's sort of convention that matrices are often given a capital letter name. So usually when we're saying let this be a matrix, we'll say like things like let A or B or capital C all be matrices. That's just convention. The notation that's really important here is if you see anything like capital A sub ij, or sometimes it won't be capitalized, you'll just see little aij, that's going to reference the element of the matrix that is in the ith row, jth column. And the really important thing about this sort of convention here is this right here. Whenever we're talking about matrices, we always talk in a row column sort of description. So whenever we say ij, so if we say 3, 2, we mean row 3, column 2. So we're always talking about the row position first and then the column position second. Okay. Size of a matrix, this is written as m times n, where m is the number of rows, again, so we always read rows first, and n is the number of columns. It shouldn't be a surprise that the reason that we use this m times m notation for the size is because if you actually take m times n and you actually multiply that out, that's going to be equal to the number of elements. Right. So if you have 3 rows and 4 columns, we would say that that's a 3 by 4 matrix. So we read it as 3 by 4, or we say 3 times 4. And that, of course, means since we have 3 rows and 4 columns, that we'd have 12 elements in there. Some very special types of matrices, well, are actually what we call row and column vectors. So if we have a 1 by n matrix, so a single row with n columns, we call that a row vector. And if we have an m by 1 matrix, meaning a matrix with only 1 column but m different rows, we call that a column vector. So in other words, this is basically saying is that vectors can be thought about as a very special type of matrix. When typed out, so generally the convention I'll try to use when I'm typing out these documents you guys are reading over are that we try to usually put vectors into bold font. So if you see something like a V like that that's in bold, that usually indicates a vector. However, I believe your textbook also generally tries to do that, but just keep in mind that when working with matrices and vectors, you can usually figure out what's being talked about. Are you talking about like a scalar, meaning just a number, a vector, a matrix? Usually just based on the context. A lot of times, talking about anything else wouldn't make a lot of sense. So we'll try to have, very consistent notation with your textbook. So a lot of capital letters for matrices, a lot of bolded letters for vectors, and everything else would just be a scalar or a single value. But just be aware you can usually deduce what's going on based on the context. A very special type of matrix is an n by n matrix, meaning that it has the same number of rows as its number of columns. It should be pretty clear that since the rows and columns are equal, if you look at it visually, it's going to make a square. So we call those square matrices. Square matrices are really important because there's a lot of properties, names, and different things that we'll be doing that only apply to square matrices. Throughout this course, we'll look at both non-square and square matrices, but there are certain things that apply only to square matrices, so it's a very important sort of designation. Finally, last sort of basic definition here is what does it really mean for two matrices to be equal? It should be pretty clear what it means, but very mathematically, there's sort of two conditions that have to hold. So two matrices A and B are said to be equal if both of these conditions hold. First, A and B have to be the same size, so they have to have the exact same size, m by n. And the element in the ij position of A has to equal the element in the bij position for B for all 1 less than or equal to I less than or equal to m. So it has to hold for every row position and every column position. So this is just a very formal way of saying that every element in A and B match, and the two matrices have to be the same size. So that should be very clear that makes sense for what it means to be equal as a matrix. Okay, so a lot of terms there. Let's take a look at just a quick example. Most of this should be probably either review or pretty clear, but again, let's just take a quick look at an example here. So here's two matrices. This is what we mean by matrices. This is how you'll see them right now. We have matrix A, which is 1, 2, 0, negative 1, root 2, E, and matrix B, which is 2, 0, 0, negative 1, negative 2, 3, 0, 0, 0. So we're just going to make sure we're comfortable with all the basic sort of statements and definitions we made. We're going to state the size of each of these, determine a couple elements, A1, 2, A2, 1, B3, 3, and then we're going to decompose A into its component column vectors and decompose B into its component row vectors. So let's go ahead and do this just sort of real quick. So for A, matrix A, of course, it has 3 rows and 2 columns. So matrix A is a 3 by 2 matrix. And matrix B is got 3 rows, 3 columns. So it's a 3 by 3 matrix. And that means that matrix B would be considered a square matrix. Okay. Let's determine some of these elements. So let's do these in different colors so we can just find them. A1, 2, so we read that as row 1, column 2. So that would be right here. That would be equal to 2. If we wanted to do A21, notice the order matters. A21 is going to be row 2, column 1. So that's going to be right there, which is 0. And if we just pick ourselves out one more color there, then B33. Well, B33 would be the 3rd row, 3rd column right there, which would be equal to 0. Okay, so just so you can sort of match those up there. You will often hear on a square matrix, and we'll talk a little bit more about this, that these elements here, everything in this case in the 1, 1, 2, 2, and 3, 3 position, those are referenced as the diagonal of that matrix because they're things that lay on the diagonal of the matrix. And you can remember the diagonal of a square matrix is anything where the row and column position are equivalent. There isn't really such a thing as the diagonal of a non-square matrix, so already there's sort of an idea that only applies to square matrices. All right, let's talk about the component. We went back a little too far. There's 0 there. Let's talk about the component column vectors for A. So those we can call those sort of A1. Hard to bold it while sort of writing there, but we can call this A1, which would be 1, 0, root 2. That's its first column, and A2 would be 2 minus 1E. So we can think about A as being made up of these two column vectors. Notice then that we could say that A, capital A, is equivalent to A1, A2. And notice that what that's basically doing is it's phrasing A as a row vector where each element in the row vector is a column vector, right? So again, this is where you're saying that when you're talking about matrices, the objects could be anything. So here's an example of where we can think about matrix A as a row vector where each vector or each element in that row vector is actually a column vector. You'll notice also that when I was talking about the column vectors, I'm not using the double subscript notation because that would reference a single element, and we were just trying to write them as column vectors. We can also decompose matrices into their row vectors, and you can do it either way. So for B, we'd have B1 be equal to, looks like 2, 0, 0, and then B2 would be, looks like -1, -2, 3. So -1, -2, 3, and then B3 looks like it would be a 0 vector, so 0, 0, 0. And then, of course, we could think about matrix B as being a column vector where each element of that column vector is actually a row vector, so B1, B2, B3. Okay. Again, if I was to type these out or if you were to see them in your textbook, these would be bolded to sort of remind you that actually they're not single elements, they're actually vectors. So there we go. That's just thinking about decomposing and thinking about these sort of matrices in terms of their component row or their component column vectors. Okay, so that's just sort of some quick practice about the basic definitions there. All right, let's continue on with some more definitions. So the first thing that is sort of really important here is the idea of a transpose, right? All that other stuff was just sort of terminology about matrices. The transpose is the first sort of matrix operation that we're going to talk about. And the transpose is really, really sort of interesting here because it's an operation that only really makes sense for matrices. In section like 2.2 and beyond, we're going to learn how to do all your basic sort of operations like addition, subtraction, multiplication, all that sort of stuff to matrices, right? All the standard arithmetic operations. But the sort of first operation I want to talk about is one that is unique to matrices. So this is what's called the transpose. So the transpose of a matrix, it applies to any sort of matrix. So the transpose of an m by n matrix A is the m by n matrix. So notice it flips the number of rows and number of columns. It's written as A with a exponent as a capital T denoting transpose. It's not actually a exponent, it's just a superscript. And it has elements defined by that the ijth element of the transpose is the ji element of the original matrix. So what this does is this flips, or maybe not flips, let's say interchanges is maybe a better word. This interchanges rows and columns. So in other words, the rows of your original matrix become the columns of the transpose, and the columns of your original matrix become the rows of the transpose. That's just saying that exact sort of thing from English into an actual mathematical statement. So let's go ahead, take those two matrices that we had from earlier and determine the transpose of each one and then state the size of the transpose. So for A, we would have A transpose. So what we're going to do is we're going to take the sort of rows of this and turn those into the columns of the transpose. So the first column of the transpose would be 1, 2, then 0, -1, then root 2, and E. So we would notice then that I did it by taking the rows of this and changing them into the columns of this. You could also look at the columns of this. First column here became the first row here. Second column here became the second row here. Either way, you're going to get the transpose there. Notice also that A transpose now is a 2 by 3 matrix, which makes sense because A was originally 3 by 2. So doing the transpose is going to flip the number of rows, number of columns. You can also, for fun, just confirm sort of manually what this is actually saying here. If I look at A transpose IJ, let's do it in a color so we can make that a little bit easier. Let's just pick one for fun. Let's do A transpose, 1, 3. So that would be this element here would be equal to root 2. And that should be equivalent to A3, 1. So the one in row 3, column 1 of the original matrix A. And if we look back over there, row 3, column 1. Yep, that was root 2. So you can actually see that that's the by element definition. We're just manually moving each of those. Much faster, obviously, to just use the visual trick of taking the original columns and making them into rows, or the original rows into columns. But just wanted you guys to sort of see that as well. Okay, let's go ahead and do the transpose for B. So B transpose. So we take the first row and turn it into the first column. So 2, 0, 0. Then we take the second row and turn it into the second column. So -1, -2, 3. And then we take the final row and turn it into the final column. So 0, 0, 0. You will notice that B transpose is still 3 by 3. It's still a square matrix, which makes sense because obviously if you have the same number of rows and columns, if you change them, well, if you interchange them, it's not going to change how many there are. We can do the same sort of confirmation. Let's just pick one for sort of fun. Let's say B transpose at 2, 1. So the 2, 1 element of the transpose. So that would be right here. That is supposed to be 0. And that should be the same as the B1, 2 element. So first row, second column of the original one. And yeah, there it is. Okay. Notice another interesting thing about the square matrix, right? Square matrix, like we said, has a diagonal. It has all those things, in this case, the 1, 1, the 2, 2, and the 3, 3 position. Notice that those don't change under the transpose, because if you're in a position where your row position and your column position are the same, the 1, 1, the 2, 2, the 3, 3, then interchanging it is going to keep it in the same spot. So the diagonal doesn't change under the transpose. That's sort of an interesting sort of idea there. All right, let's continue on with some more descriptions. Our next set, though, are all going to apply to square matrices. So we're going to start talking about some special designations for square matrices. So this group of definitions all apply to n by n square matrices. First, a property of a matrix. So this isn't a matrix operation. The transpose is an operation, right? It takes a matrix and it applies this operation and gets another matrix. This is more a property of a matrix. It's called the trace of a matrix. Again, everything we're talking about only applies to square matrices. It's written as TR of A, and it's calculated as the sum from k equals 1 to n of the AKK elements, meaning it sums up the diagonal elements. So this is the sum of the diagonal elements. So if you ever see the trace of a matrix reference, that just means you're summing up the diagonal elements. All right, next definition is a matrix A is said to be upper triangular if Aij equals 0 whenever I is greater than j. So what does this mean? Well, this means if your row position is ever larger than your column position, which if you think about it, row position being larger than your column position, if you have a matrix, diagonal is where they're equal. So we want row position to be greater than column position. That means down here, all that has to be 0. You can see then visually why we call it upper triangular, right? It's upper triangular because the values, the only thing that's non-zero in the matrix, all form an upper triangular, things at the diagonal or above it. Very similar, a matrix is said to be lower triangular if Aij equals 0 whenever I is less than j. So again, there's a matrix. The diagonal elements are where I equals j. I being less than j means that your row position is less than your column position, which means you're in over here. So all this stuff must be 0. So in other words, the only non-zero stuff is over here, which is again why it's called lower triangular. Very, very sort of special one. A matrix is said to be diagonal if Aij equals 0 whenever I doesn't equal j, meaning that a diagonal matrix is one whose only non-zero values exist on the diagonal, and everything up here is 0 and everything down there is 0. So a diagonal matrix literally only has non-zero values on, or it only has its non-zero values on the diagonal. Could also have zeros on the diagonal, but it must have zeros everywhere else. All right, two last things that sort of start to put some of these definitions together. A matrix A is said to be symmetric if the transpose of the matrix equals itself. So it's symmetric if when you perform the transpose, you get the same matrix back. And a matrix is said to be skew symmetric if when you perform the transpose, you get the negative of the matrix. Now, it's a little unfair to make this definition here because we don't technically know what we mean by the negative of a matrix, but it shouldn't be too hard to believe that the negative of a matrix just means that we negate every element in the matrix. So you're skew symmetric if when you apply the transpose, it's the same as just negating every element in the matrix. Okay, so this is a lot of definitions here. Let's take a look at a couple examples of classifying different matrices based on these. Are there some matrices where none of this applies? Yeah, for sure. There are definitely tons of matrices out there that are not upper triangular, lower triangular, diagonal symmetric, or skew symmetric, right? So it's definitely possible that you're none of these things. But let's go ahead and take a look at some classification. So here's 3 square matrices. We can just make a note real quick here. This one is a 3x3 square matrix. This is a 2x2 square matrix, and this is a 4x4 square matrix. What we want to do is first we're going to go through and talk about if each of these matrices are upper triangular, lower triangular, diagonal, or none. Then we're going to state if the matrix is symmetric, skew symmetric, or neither. And then finally we're going to calculate the trace of each of these. So let's look at A. So for A, the first thing we want to know is it upper triangular, lower triangular, diagonal, or not? Well, we can definitely throw out diagonal because we see that there's like this 1 and this 5 here. Those are not on the diagonal and they're equal to a non-zero value. So this thing's definitely not diagonal. You can notice though that everything sort of lives above, everything that's in terms of non-zero is at the diagonal or above, meaning that A is an example of an upper triangular. It is not lower triangular and it is not diagonal. So we can rule those out. Let's do the same for B, then we'll come back to talking about symmetric, skew symmetric, so we'll just focus on the same thing. For B here, again, not going to be considered diagonal because we've got non-zero values off the diagonal, so it's definitely not diagonal. It can't be lower or upper triangular because we have a value here and we have a value there, a non-zero value there. So this one is none of these, so it has none of those classifications. And then for C, well, you can notice that the only non-zero values lie on the diagonal. So this is a diagonal matrix. And this is sort of interesting. If you're a diagonal matrix, you are automatically upper triangular and lower triangular. Because if we think about it, we could sort of say, well, all the non-zero values live in the upper triangular. But since they also live on the diagonal, we could also say they all just live in the lower triangular. So this is a very sort of, just interesting little idea here. If you're a diagonal matrix, you are also simultaneously upper triangular and lower triangular. In fact, we could have defined diagonal. It wouldn't have been a great definition, but we could have done it as diagonal means you are both upper triangular and lower triangular. So C is an example of one that falls under all 3 classifications. Okay, now let's talk about symmetric and skew symmetric. So to do that, let's determine the transpose of each. So A transpose would be 3, 1, 0, 0, 2, 5, 0, 0, negative 3. Now, clearly, A transpose is not the same as A, so we know that symmetric is out. And if we imagine negating this, we get something like negative 3, negative 1, 0. That doesn't look anything like this, so it is also not skew symmetric. So that's out as well. Let's look at B. B transpose looks like it'd be 0, 5, negative 5, 0. Now, pretty clear that that's not the same as that. So this one is not symmetric. But if we were to negate this, we'd get 0, negative 5, which is exactly what we have, and then 5, 0, which is exactly what we have. So this is skew symmetric. So B is an example of a skew symmetric matrix. It's a skew symmetric matrix because when we take its transpose, we get the negative of the original matrix. All right, and let's look at C transpose. Well, it would be 2, 0, 0, 0, and then 0, 0, 0, 0, and then 0, 0, 1, 0, and then 0, 0, 0, negative 6. So there we go. That is identical to this. So this would be one that is symmetric. And of course, if it's symmetric, it's not going to be skew symmetric because it needs to be itself, not its negative. So it is definitely not skew symmetric here. Okay. Last thing to do is calculate the trace of each of these. So trace of A, well, that would just be adding up the diagonal elements. So it would be 3 plus 2 minus 3. So it looks like trace of A would be equal to 2. So notice that the trace is just a number, right? It's not a matrix or anything. It's just a number. It's a property of the matrix. The trace of B is 0 plus 0. So trace of B is 0. And for trace of C, we're adding up the diagonal elements. So trace of C looks like it would be 2 plus 0 plus 1 plus or minus 6. And if we add those up, it looks like trace of C is negative 3. So we got trace of A is 2, trace of B is 0, and trace of C is negative 3 there. So there we go. We just went ahead, confirmed whether or not these were upper triangular, lower triangular, diagonal, none, symmetric, skew symmetric, neither, and we calculated the trace. So that just helps you guys practice all those definitions in terms that we just mentioned there. All right, last thing to say for our brief introduction into matrices here before we start talking about matrix operations is what is a matrix function. So a matrix function is very simple. It's simply just this sort of name that we give to matrices whose elements are functions of some variable. So as an example of that, we can consider the matrix function a of x, defined by a of x equals x squared e to the x 1, 2x 0 ln x. So this is a 2 by 3 matrix function, 2 rows, 3 columns, where these things are all functions of x. Now, some of them are obviously constant functions of x. Other ones are more interesting functions of x. If you are asked to evaluate a matrix function, so like a of 1 in this case, just means you evaluate each function at x equals 1, and then that makes a matrix of real or of scalar values here. So in this case, that matrix would be 1e1, 2, 0, and then ln of 1, of course, is also 0. So there would be a of 1. So the output of a matrix function is a matrix, which should make sense, right? A matrix function is just made up of elements that are functions. So their output, each one is going to output its own individual value, which means that the overall matrix function at a particular value is a matrix. And of course, it's a 2 by 3 matrix because it's not going to change the size. Okay, so this wraps up our brief introduction into matrices. In our next video, we'll actually start talking about applying operations to matrices. So we'll begin our discussion with learning how to multiply matrices by scalars, as well as talking about addition, subtraction, etc.